Okay, hello everyone. And in the last lecture, we mainly learned about a search heuristic, which is a key component of symbolic execution for mitigating the path explosion problems. So in this lecture, we will learn another white box testing method for deep neural network. Actually, this research topics about testing deep neural networks has recently been attracting attention in the field of software engineering. So this research area is still at early stage. Let's start with this week's lectures. So today I will first motivate the need for the deep neural network testing by asking the question, why should we test DNNs? And then to explain how to test a given deep neural network model, we first learn basic terms for DNN, such as layer, neuron activation function, or output value of layers, and so on. And then, so I will define the deep neural network informally, and then after learning the terms of the DNNs, and we learn the general goal of testing DNNs. And then finally, we will learn how the white box testing method of DNNs works briefly. Okay, let's start. So as you know, deep neural networks are everywhere in the world. So for example, DNNs are used for diverse domain applications such as image classification or game playing, natural language processing, healthcare, and so on. In particular, in terms of game playing, DeepMind's StarCraft playing AI is able to beat 90% of the human gamers. So this is really surprising result. And actually, while I was preparing the lectures, I found two recent interesting cases for the usage of DNNs. So the first is the case of Google AI system, namely Duplex, automatically calling a restaurant and making a reservation through a natural conversation like humans. So let's listen to the conversation used for the actual reservation provided by Google. Let's listen.
Hey, I'm calling to make a reservation. I'm looking for a table on Friday the 4th.
This Friday?
Yeah.
So, how many people? 5?
It's for 2 people.
For 2?
Yes.
And what time do you welcome?
At 7 p.m.
7. Am I your name?
First name is Yaniv, Y-A-N-I-V.
Okay, I got it. So it will be 2 people at 7 o'clock.
Yes.
Okay, got it. Yeah. Thank you.
Okay, awesome. Thanks a lot.
Thank you. Have a good night. Bye.
Okay, bye-bye.
Isn't it really amazing? So for me personally, it feels like a human being, not a machine. And the second case related to a research paper published in CBPR 2 years ago. This research is a technology that interactively changes the basic drawing on the left side to a nice picture like the one on the right. I also bring a short YouTube video about this interactive image synthesis. So let's look at this video shortly.
Our interactive application looks like a simple paint app. However, instead of color palette, we have semantic palette. Let's pick a label and use the fill mode to replace cloud with ocean. Some cliff rock will be nice. Let me make the scene more interesting by adding a small rock and a faraway mountain. You can apply different styles to the image by regenerating those style codes or by stealing styles from guide images. We continue drawing by adding a small beach. Trying different styles or trying different semantics.
In addition to this very interesting use case of DNNs, DNNs are also used in safety critical domains. As we all know, DNNs mounted on self-driving cars can have direct impact on our lives. Likewise, in medical diagnosis, the incorrect behavior of DNN can cause misdiagnosis of our body, which can lead to fatal result. So we need to thoroughly check whether the deep neural network is safe enough for us to use in diverse applications, in particular safety critical applications. What do you think about the safety and reliability of the DNNs? In academia, especially in the field of software engineering, the answer is no. According to the deep test published in ICSI 2018, the deep neural networks equipped in autonomous cars often demonstrate incorrect corner case behaviors that can lead to potentially fatal collisions. Let's look at these pictures. As you can see, DNN is correctly guiding the driving direction for the original image on the left. However, deep test reported that for the mutated image on the right, such as changing the weather like rainy day or cloudy or even sunny day, DNNs are suddenly guiding driving in a really dangerous directions. And deep test, as well as many research works in academia, in particular in software engineering, are reporting that DNNs are still unstable and dangerous. And what about DNNs used in the industry? Many companies such as Tesla and Google's are actually used in DNNs for self-driving cars. But despite the tremendous progress, just like traditional software, DNNs equipped in self-driving cars often show that unexpected behavior that lead to fatal crash in the real world. I brought some recent articles about self-driving cars accident. For example, the article on the right happened in the last year reported that the Tesla autopilot failed to avoid an overturned the truck even though the driver hit the brake. So both in industry and academia, ensuring that deep neural networks behave as expected is an urgent issue in nowadays. Now you are sufficiently motivated about the need of DNN testing. So let's move on to the next question. What is the goal of the testing DNNs? Put simply, this goal might achieve high code coverage or find many bugs, just like traditional software testing we learned before. However, testing traditional software is different from testing DNNs. According to Deep Explorer presented in SOSP 2017, using only 10 randomly selected inputs can achieve 100 code coverage for all DNNs. In this work, the code coverage denotes the line coverage of the Python code used in training and testing process for each deep neural network models. And as you can see in this table, across the diverse datasets such as MNIST, ImageNet, and the diverse DNN model, shortly say C1, C2, C3, achieving full coverage seems to be really trivial, as we just need to 10 randomly selected inputs. So my question is, why is it so easy to achieve this in DNN testing? As we learned in the previous lectures, achieving 100 code coverage for real-world programs in the traditional software is nearly impossible. So what differences between DNN and traditional software leads to this result? The key reason is really intuitive reasons. The decision logic in DNNs is embedded in namely neurons and layers, not in the code. So in traditional software, the software developers have manually written the decision logic on the code having control flow. But unlike conventional software, in DNNs, the decision logic is determined by the neurons and layers and their weight. In other words, testing DNNs corresponds to testing the internal logic of DNN, not the Python code surrounding the DNN code. So for this reason, designing DNN-specific coverage metrics that can check whether the internal logic of DNN is thoroughly tested has become an emerging research topic for DNN testing. So starting from the neural coverage, many different coverage metrics for DNN, such as top K neuron coverages and K multi-section neuron coverage and surprise coverage and value sign coverage have been presented in the top tier conferences like SOSP, ICSI, and ASD. But note that this research field is still at the early stage, and so to introduce some coverage metric for DNNs, I will first briefly introduce DNN and the terminologies used in DNN, although everyone may know these terms. For presentation simplicity, I will focus on explaining fully connected neural network on the right. And we will informally learn the terms like layer, neuron, weight, and output value of layer, and activation functions, and so on. So first, a single deep neural network consists of a set of layers. And there are three kinds of layers: input layer and hidden layer and out layers. And first layer corresponds to an input of DNNs. And the out layer means the last layers of deep neural network. And all the layers between input layer and out layers are called hidden layers. So this fully connected neural network consists of 4 layers containing 2 hidden layers. Next, each layer consists of a set of so-called neurons. In particular, the first layer corresponds to an input vector of real numbers. And in this case, an input vector has 3-dimensional real number vectors. And the second layer consists of 4 neurons from 2n to 1 to n to 4 in this case.